Thank you. So unfortunately, the main statement is a conjecture and not a theorem yet. And but I hope to convince you that it's interesting anyway, and to try to. I would be happy either way, if it's proven or disproven. So here is a information theory in one slide. Basically, what is information theory? It's developed to understand basically one-way data transmission, and within that world, we have pretty much all the answers. And the issues that are usually studied are, so there is Alice, she wants to communicate to Bob. Also, storage actually is in the same category, which is just future Alice. And the issues usually addressed within this context include noise, channel efficiency, so how much communication you need to transmit what you have to transmit, computational issues, and today we'll focus on questions of efficient communication in terms of compression, so there is no noise, everyone is computationally unbounded. Within one-way communication, this is essentially a solved problem. For example, by Huffman coding, if we have a random variable x and we want to transmit it, we know exactly how many bits on average we need. So it's at least the entropy of x, and this is true pretty much in any reasonable imaginable model. And if you want to just transmit zeros and ones, you can do it with a prefix-free code and pay an extra additive 1 bit and always succeed. And even more complex one-way settings where there is shared priors and correlations. So the one-way setting is pretty well understood. And what we want to talk about is the interactive setting of two parties. So Alice and Bob, so basically the story in the first 3 slides was Alice has a message. It's not very informative. It has low entropy. And can you compress to essentially its entropy? The answer is yes. Now Alice and Bob have a conversation. They don't learn too much from that conversation. It could be long but not very informative. Can we shorten it? And basically shorten it to its information content, which needs to be defined. So the information content of a protocol, I mean, if you're comfortable with this notation, this is the formula. If not, it really doesn't matter. Basically, it's defined so Alice and Bob have inputs x and y distributed according to some prior. And they engage in a protocol that is also a random variable. So the outcome of a protocol is a random variable. And you ask Alice, OK, from this conversation, how much did you learn about y? How many bits of information, given that you know x already? So this quantity, it's important to realize, depends both on the prior and on the conversation. So one, to think about a couple corner cases, if pi is empty, then this is 0. If x and y are distributed on the diagonal, so x is always equal to y, it's 0 regardless of what they say, because they have nothing new to teach each other. OK, so basically, if you want to talk about compression, this is the ultimate question. How much information communication is needed to simulate a protocol pi? And by simulate, I mean you can quibble about definitions, but basically here is what I mean by simulate. They can talk. In the end, they need to output, they can use shared randomness for free. And in the end, they have to output 2 strings that are equal with high probability and that are distributed roughly as pi should have been distributed. So for example, you can take this and plug it anywhere where pi was needed before. So it has the same functionality up to epsilon. And the relevant parameters are the information cost of pi. So this is I. So this we'll call it I for the rest of the talk. And the length, the number of bits in the original protocol pi. And OK, so it's an easy fact that I is less than or equal to C. So you never teach each other more than you talk. And this question is really interesting when I is much less than C, because if I is equal to C, then this is already a very informative conversation. You cannot hope to compress it. So you should think of I as being much, much smaller than C, even as small as logarithmic. So, okay, so some basics. So the obvious upper bound is C. So you can simulate pi, you can execute pi and pay C. And it's an easy, but not obvious, but easy lower bound that it's at least I. It's like saying that you cannot hope to transmit data in less than h of x, less than the entropy. And another fact that as n goes to infinity, essentially all protocols become compressible. And the reason for this is essentially if you take many copies of pi, eventually it stops being a very interactive problem because it becomes, the number of rounds becomes dominated by the amount of information, at which point the one-way machinery kicks in. And okay, so but what it does, it leads to very tight connections. So one of the original reasons for studying this problem, even though in some sense I think it's a more interesting problem than the direct sum problem in communication complexity, but this is a very old problem from the 80s, and it was one of the original reasons for studying this compression problem. So just to orient you, so better compression results mean stronger randomized direct sum. And better incompressibility results, so examples of problems that are hard to compress, immediately lead to stronger violations of direct sum. So let me try to convince you of the second statement. So suppose you have some conversation that is very hard to compress. So, and we can define the task of simulating pi and look at t to the n, the task of simulating n IAD copies of pi. So as I mentioned on the previous slide, eventually when you take many copies, it starts scaling the cost of simulating many copies of pi. Eventually will scale like I, and actually eventually means roughly C. So after you take C copies, you can simulate it in I times C, but one copy takes much more than I by incompressibility, so you get a violation of direct sum. So it's an if and only if type of statement, and it's if and only if in logical terms, and it's also an if and only if in quantitative terms. So better there means better there. Okay, so what do we know about, so back to the question of protocol compression. So we have a conversation, not very informative, pretty long. We want to shorten it. So we want C prime to be less than C, much less than C. So this is trivial. The two best general results we have, one says that you can compress to something like the geometric mean of I and C. So this is still polynomial in C, but it's considerably better. And there is another result that says you can compress to exponential in I without any dependence on C. So at least it tells you that even very, 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 very long conversations can be, if they're not informative, you pay at most the exponent of I. And this is useful sometimes when you have a finite problem, for example. Okay, so in terms of hardness, we have a series of works by Ganor, Cole, and Raz that show something like this, that there are problems where the dependence on I is excellent. It's as high as it can be. It's exponential. So basically, those results settle the dependence on I, but the dependence on C is only logarithmic. So it's something because the hard to compress tasks that they exhibited were extremely, extremely long. The lower bound you get is only of this form. So it's very hard in I, but if I'm willing to pay even log square C, I think it's actually breakable. So those examples are actually, you can compress to log square C just because of the way parameters works, because log square C is bigger than 2 to the I. But this at least settles the dependence on I, and it rules out the strongest possible direct sum theorem, which says that any task repeated n times is at least as hard as n times one copy. That's off the table now, but this is still possible. So somehow it's very impressive in I, but in terms of direct sum, this is what it buys you in the very end. And the hope is, so on the other hand, the best we have in the other direction is something like root n here. And the question is, so I personally believe it should be some power of n smaller than 1, but that's where we stand. And our goal now is to get a candidate So at least something that's super polynomial in I times log C. And actually, there is no reason to believe this example doesn't buy you some polynomial in C and exponential in I. So with K being something like a quarter or 1/8. And I think if you can prove some constant, you'll get to the optimal constant, which could be either 1/2 or 1/4. But it's delicate because, so for the experts, so if all the previous results hold also for something called external information cost, which is the quantity of what an external observer learns, which is usually more than what the participants learn. So all the previous results were lower bounds for that case as well. And now you cannot hope to use those lower bounds because actually there you have a compression that is like I polylog C. So if you want to beat I polylog C or even approach something like poly C exponential in I, you definitely have to work with something where the external information cost is high. Okay, so I'll get to the example. Just so this is already part of the construction, but this is not a unique part. This is just what is a protocol. So this is any protocol. So Alice and Bob are given a binary tree of some depth C, and which is labeled with numbers, which will be the transition probabilities. Alice owns the odd layer nodes, Bob owns even layers, and they're given correlated transition probabilities. So on each node edge, whether you own it or not, there is a number, and those numbers are correlated. And the goal is to sample a path according to the owner's probability distribution. So here, usually we call the probabilities of the owner P and the probabilities of the other party Q. So the goal is to sample, for example, this path with probability P0, 1, this times this, because Bob owns this node. Okay, so the Qs play no role in the actual execution, but they play a role in measuring information, and the task becomes easy if those numbers are close to each other. So imagine, for example, if you were guaranteed that P is equal to Q always, you don't need to communicate at all. You can just use public randomness. All of them know the exact distribution of the leaves, use public randomness, and go home. And in general, the information cost of this task is the L2 distance along an expected path, essentially, up to. So that's how it behaves. And a lot of the fun that happens around this area is because L2 distance is L2 and statistical distance is L1. Okay, so we take a tree of depth. So this is now the excited tree game. We have a tree depth C. We pick a parameter, think of it as some polylog C. And each node is picked as special with probability K over C. And then we take along each path from root to leaf, we take the first special node. So think about it as there is some process that dies independently IID with probability K over C, and you look at each branch where the first time it's terminated, it breaks down. So this is S, and we call nodes above S not excited and nodes below S excited, and the goal is to sample only up to S. So you want to sample from some distribution that I'll tell you about up to S. And so here is the distribution. So we take two uniform distributions, mu1 and mu2. Mu1 is on a pretty short interval, and mu2 is on a much longer interval. If the node is not excited, then P and Q are very close to each other. They differ just by x1 or twice x1. And if a node is excited, then they differ by x2. And note that if you are just one party, but just by looking at one of those numbers, but not both of them, the distributions of excited and not excited look exactly the same. Okay, so now, and the goal is to sample, correctly sample distributions stopping at S. So up to S, the information cost of each step is about k squared over c. So we should expect the information cost up to here to add up to something like k squared. And the moment you're past s, it becomes pretty high. It becomes, because this difference is now distributed according to some power of c, it becomes something like 4th root of c per round. So think about it as the process where Alice and Bob talk to each other, and they have a very good understanding, so they can talk easily. At some point, something goes wrong, and then it's like they're from different planets. They can't understand each other, so it gets much harder to make progress. So this is the process. And there are two parts to it. So one part is a theorem that it in fact, this is not exactly a protocol because I told you to stop at S, and of course Alice and Bob are not going to get S. If they get S, this is a very easy problem. So they're not getting S, but it's not hard to see that basically you can simulate and use estimation algorithms. There are generic algorithms like to basically simulate this problem in polylog C in k square information. So the communication cost is C, the information cost is polylog C, and we don't have so basically we have no indication that you can solve this problem faster than poly C, than something like C to the 1/4 or 1/8, which would actually yield something like this. And okay, so there are three possible, so I have like 1 minute. So there are three possible outcomes, two of which will make me happy. So one outcome is that someone proves that this is a hard problem. It will pretty much settle the information compression, the interactive compression problem. Another good outcome is someone breaks it gracefully. So this fact, so not being able to find this S actually is, in some sense, the main obstacle to applying many existing techniques to compression. So if you break, so basically the generic make progress by joint sampling, by rewind and mix is exactly what we don't know how to do. And if you manage to break this example like that, then we probably will get compression. So, and this will lead to some direct sum results. The third kind of less desirable outcome is that you exploit the idiosyncrasies of this problem to just break it without teaching us something global. But then still, we might be able to tweak it. And we tried, so it might be hard. So without getting some new insight, it's possible, but it would still be interesting. So that's basically the question. So it depends on you potentially can get lower bounds for multipass. So it depends. So I think in the typical applications, no, but I'm not sure. It's a very broad question. So it depends on how your memory is used, I think.